like first derivative of an interesting effective action, which now like as an out. So I just rewrote it in a way when it's often introduced. So there's a mass term which is called R here, which is just the combination of that we found that has an interesting property of changing the sign. And then I introduced here the correlation length, which is 1 over P Fermi, essentially apart from the factor, and then the rest of it. So now, as an outlook, well, what one can do here is now go through an RD analysis to look at the fluctuations, the renormalization due to fluctuations, and see what they do to the mean field solution fluctuations. But this is, left for, let's say, if we continue. What we can still do is like to return to our mean field analysis. So once we have this action here, which is a kind of Innsbruck-Landau theory now for the case that we're interested in, we can look at the free energy or at the action for constant and static fields. So now imaginary time dependence and just homogeneous contributions where it's a derivative and this is just 0. So where the action is given by this. Okay. So let's study this and then look like at the phase diagram, which should actually give us again the phase diagram that we also found from the mean field analysis. But let me just make one comment, which I don't recall if I already made it. So we can look at this action and consider the classical free energy. And I will, what I want to do is comment again why this is called classical free energy. Now here of homogeneous fluctuations. That we already considered in the ANLAT for the mean field equation, so where M is just some value, mean field value, and we just have the Q for momentum equal 0 component. So we can make an analysis of the classical free energy, which you can define as the effective action multiplied by temperature and divided by site. So this would be action per site multiplied with the energy by the temperature. And what I just want to comment here is like, why do I call this classical? So here I really mean the free configurations, okay, that are homogeneous, but classical here refers to the fact that I consider like the static configuration. So the omega m equals 0 Matsubara frequency. So why do we call this classical? So this would be where this term doesn't appear. So I think we already commented on this like several times. So what did we do? Like in this case, we started out from a path integral representation of the partition function. So we have a trace e to the minus beta h bar, where h bar is the Hamilton operator. So we do all the path integral trick always to like somehow be able to deal with operators. And we do them by substituting operators by some numbers, okay, which is then the action. But what we have to do is we have to pay a price for it, because in the construction, in order to substitute the operators by numbers, we always have to introduce some time. So in the quantum mechanics problem, we saw that going from a point particle, you can represent the propagator in terms of integrals over just fields or this coordinates path in this way. So where operators do not appear anymore, but the price we had to pay is that we go from zero-dimensional objects to this path, so to one-dimensional object. So in the same way here, in the statistics formulation of the partition function, we go from a d-dimensional fields in general to d plus 1, where the plus 1 refers to the imaginary time fluctuations in the construction. Okay? So we account for the non-commutativity by introducing, or we get rid of it by introducing an extra degree of freedom, which is the fluctuations in imaginary time. Okay? So this means if we consider the static contributions in imaginary time, what we are doing in a way is just to consider the classical content of the field. Okay? Because this is like saying, well, we didn't start with a Hamilton operator, but with a Hamilton function. Okay? So there's always like the classical limit. You can also see it like, because the d tau has an integral 1 over t, so if t is very large, we expect that we have some kind of classical limit, and we see that then typically for large temperatures this time interval is small, so then the imaginary time fluctuations are just suppressed. Okay? So this is why I say here classical free energy, because we're considering like the classical. So if we look at this, then this action is just given by what? mu0 r m squared minus mu0 12. Okay, so this is just copying the action to these considerations. So we can make a plot of the free energy as a function of the modulus of m. Okay, and this is now just repeating like what I tried to explain before. So if r is positive, and we accept that for the 3D case and the quadratic dispersion, this here is negative, so all this is positive. We just have an m bar squared plus m bar 4, so this is just some function which has a minimum at m equals 0. Okay? So this would be for r larger than 0. Now if r equals to 0, this becomes just very flat here, because this is in proportion to the m to the power 4. So this will then be something like this. And something interesting happens once r becomes negative, because at small m this is then dominated by the m squared term, and for large m it's dominated by the m4, which guarantees the overall stability. So if m becomes negative, it first goes down and then goes up. So probably this should be still outside this one here. Makes sense. Okay, so you build up, once r becomes negative, you build up minima, which then become more and more pronounced the more negative this becomes. And it is this minima which are the solutions of the mean field equation that we found. Okay? So we considered the limit where m just starts to get a mean field solution which is different from 0. Okay? So now from this stability, from this effective action, where we have also the fourth order term which always guarantees the stability, we can see that the minima, well, are from minimizing this expression here. So the minima are, well, the minimal values are plus minus 6r mu0 divided by second derivative for r smaller than 0, and 0 for r larger. Okay. So we see that indeed in this scenario we have a continuous building up of a finite expectation value.
Você fica sem saber, sou apaixonado por isso. Essa paixão é impregna nos seus alunos.
So you build up once r becomes negative, so this is negative and this is negative, all this makes sense. So you build up continuously a finite expectation value. So this describes the second order phase transition that we found. Okay? But the requirement for this is that the second derivative of the density of states is negative. Okay? So this guarantees stability, and then we have indeed here the second order phase transition in this case. Okay, but so let's just make here a few comments. So for the density of states being smaller than 0, you have the second derivative, second order phase transition. Phase transition. And actually applies to, so this being negative applies to the case that we considered u of epsilon, which is 3D and epsilon p squared over 2n. Okay? So that was this case. Now there is scenarios where this is actually positive. Then what you have to do is then take into account the terms to m to the power of 6, which should then stabilize everything. Okay? I mean, some power has to be positive to stabilize everything. But then, this I leave like for your investigation, so I thought that probably you know this, but you can just play around with it. So if you now add here, let's say, term alpha m to the power of 6, and if this is positive, you can see that then there's, then actually what can happen is that this building up of a finite m is not continuously anymore, but happens like in a jumping way. So you convert your second order into first order phase equation. Okay, so I leave this for you, or we'll do this like in the next time, like you can see, but just comment. So if this is positive, you have to take the order into the sixth order, and then phase transition becomes first order. Becomes first order. So then just one comment to real materials. So most transition metal ferromagnets like iron, cobalt, and so on, they involve narrow bands, which means a large density of states in 3D. With large negative curvature. So this means that, so I hope you can read. So most transition metal ferromagnets, so to which the theory should apply, like iron, cobalt, involve narrow bands in 3D with large negative curvature. So this means second derivative is negative and the density of states is typically large. Okay? So we saw that what really matters is that the product of the interaction times the density of state is large. So even small u, if you have a large density of states, you make this transition then. However, in, for example, quasi-1D systems, quasi-2D systems, density of states has mostly second derivative larger than 0, and ferromagnetic transition then is expected to be first order. Okay. So this is just comment now here, quasi 2D is important because, I mean, you cannot have like a symmetry breaking in purely 2D solids. So that was just a small comment on that. And then, actually, I wanted to talk about, like, let's see. So there's some, okay, let's see. So there's some, what did we do? So we found one here example where we have some phase transition to a metallic phase and we derived effective action. So of course, one has to analyze the stability of this mean field analysis with respect to fluctuations. So like in low dimensions, you can find mean field and non-trivial mean field, but this will be typically destroyed by fluctuations because you cannot break symmetries in low-dimensional systems. Now, breaking symmetry here actually means what? So what we have derived here was effective theory starting out from a model where for simplicity we already singled out some quantization axis for spin. But we said that, well, the interaction sigma z that we started out from can be readily generalized. Like we started out from an interaction of this form and already made the comment that this is readily generalized to the scalar product of two spins, so where you don't single out quantization axis. Okay? In this case, you can just do exactly the same analysis that we did, so only the Hubbard-Satonovich field then is a vector. Okay? So there, then you can see better what it means. Well, breaking the symmetry means that if M takes a finite value, it also has some direction. And this just means that, well, the ferromagnetic order builds up in some direction. So you see that you start out from the microscopic theory, which has some rotational invariance. So this theory is invariant under rotations, all three rotations. But a non-trivial mean field will always break this non-trivial a non-trivial mean field will always break the symmetry, okay? So you have a symmetry breaking going on, and you can, I should comment on this, so probably this will then make just the next lecture, like comment on how the symmetry breaking can be understood, like why the hell you start out from an action which has some symmetry, which then is broken, so what singles out the direction of spin, so this is one thing can comment on. And then the second thing is that once, in this case, like you have, let's say, now ferromagnetic order in some direction, let's say the z direction, then what you have is you have broken your entire O3 symmetry, but you still preserve a certain symmetry. So you preserve rotations around the z-axis. So all rotations around the z-axis leave the mean field configuration invariant. So you started out from an action here in this case which had an O3 symmetry, and your mean field solutions have an O2 symmetry, which is a rotation around the z-axis. Okay, but this means that if you take the quotient of those two, this now defines a manifold of mean field solutions. So if I take this solution and operate on this with a rotation which is not a rotation around the z-axis, so which is some element from this quotient, this will just rotate all the spins in some direction. Okay, the price that I have to pay if I make the constant rotations and all spin in the same direction is just zero, because I mean the action is the same. The mean field action for spin taken in this direction and this direction is the same. So this means that I have an entire manifold of mean field solutions, and now I can start to play around and say, well, what happens if I do not make a constant rotation around the axis, but start to make like soft fluctuations, like turn all those like a little bit in this direction and keep these in the same way. So then I see that in this case the action of these soft fluctuations will not be identical to the mean field action, but will have some finite difference. However, this finite difference in the limit where I send all fluctuations to be like in the same direction, this goes to zero. So the difference should be proportional to the wavelength of the excitation or of the rotation. Okay. So if I make start out from this configuration, and now this is the spin chain where everything points in the z direction. Now I start like twisting these a little bit. and then turning here in this direction. So this could be described by some rotation which depends slightly on space, but is a function on the wavelength which is proportional to 1 over q, where q is the Fourier, at the moment, the wavelength thing. 1 over q is the wavelength of this exchange. Okay? So in the limit where this wavelength goes to infinite, means just that I rotate all by the same angle, which means q going to 0. Then I again have the same action as, oh, I'm explaining that, no? Yeah? So everything that I want to say is that if you now start to playing around with rotations from this group here, which are slightly varying in space, this gives you a soft mode action, an action which should be proportional to like q, okay, to the inverse wavelength. If q goes to 0, then this action is just the same for all the configurations. So this gives rise. So what you have started out from the symmetry of your problem. You have broken your symmetry by mean field solution, which means you have an entire manifold of mean field solutions rotating all the same way. Which means if you now make it like a game and now rotate all in the same amount but make slow variations, this gives rise to some soft mode action, Goldstone action, okay, a massless. So this always comes like one leads to the other. You break the symmetry, a continuous symmetry in this case, and then you can derive like soft mode action also. And yeah, you can formalize this a little bit, and maybe I'll comment on this. But this is then also an outlook for maybe what one can do. So one has like always a scenario that, well, if you have a phase transition going on, you can derive a low energy or soft mode action, which often is interesting. One can do this for different cases, like this was for the magnetic case. The next thing would be like to look at superconductivity. There you break, here you break an O3 symmetry. In superconducting, here you break like a U1 gauge symmetry. Then there's like in disordered systems, like disordered electrons, there's some more abstract symmetry that you break, but you can always derive then defective actions in terms of some rules about some Goldstone modes, and then make an RG analysis. That's easy to see what these fluctuations do. Okay.